Hello, welcome to my talk on monitoring in a microservices world. Quick introduction, my name is Fabian, I work for Instana. Instana is a monitoring company. We have an application monitoring product with a strong focus on monitoring dynamic microservice applications and environments. And in the next 30 minutes, I'm going to give you an introduction on the impact that Docker and microservices and Docker runtimes have on monitoring and what modern application monitoring systems do to overcome the new challenges. If you are watching this live, I am available in the chat, so feel free to ask questions during the talk and I will do my best to answer them. Let's get started. I guess most of you have heard the term microservices before. So microservices are a software architecture pattern where you take your application, your single deployment, and split it up into multiple independently deployable services. Why is this popular? Why do people do this? There are several answers for that. For software developers, having those independent services helps them to structure their software better, to divide their application into individual parts of the business domain and have clear boundaries between those parts of the business domain. And also for a specific service, they can then choose the best tools and programming languages and framework to implement that specific part of the business domain that this service provides. Moreover, the microservices approach gives you operational flexibility. For example, you can roll out an update to an individual service without the need for updating the entire application. Or if a specific service is a performance bottleneck, you can scale it out and have multiple instances of it without the need for scaling out the entire application. What does the microservices approach have to do with Docker? I think you can easily argue that Docker is the main enabler or the main facilitator or the main driver behind many microservice implementations today. So if a company these days decides to go with the microservices architecture style, in most cases, they also decide to use Docker as the underlying technology. And then they will have their services implemented as Docker images. They will have their services running as Docker containers in Docker runtime environments like Kubernetes, for example. And they will use Docker tooling, like, for example, have their engineers ship their application as Docker images and then have continuous integration, continuous deployment pipelines to bring those Docker images into production. So I would say if you look at how people implement the microservices architecture today, in most cases, this goes hand in hand with using Docker as the underlying technology. What's the impact of this development on monitoring? And of course, in the most part of this talk, I will talk about challenges and new things that became complicated and new ways to overcome these challenges. But if you look at it, some things actually became easier with the introduction of modern runtime environments. And interestingly, some of the things that became easier now or that are now commodity used to be core tasks of monitoring a few years ago. Think, for example, of health checks. A few years ago, writing health checks for your application in Nagios was one of the core tasks that we typically associated with monitoring. Today, platforms like Kubernetes provide health checks out of the box, and they basically have become commodity. Also, runtime platforms provide information on service orchestration, so you can just use this information in your monitoring system. However, of course, some things have become harder. And one of the things that makes monitoring harder is that these environments change a lot more dynamically than static deployments of single applications. Um, and these dynamic changes have many dimensions. So if you allow your engineering teams to ship services into production, then you will have a much higher rate of new services being deployed, right? If you have automatic scaling depending on the load, then you will have a high rate of services scaling out and scaling back again. If you have overlay networks, then you will have a high rate of changes in the network technology, because defining a new service might, introduce new network routes, new IP addresses being generated on the fly, etc. And what that means for monitoring is that automation is key to handling these changes. Whenever you have a manual step associated with any of the changes happening in your system, this manual step will at one point become a bottleneck, uh, slowing down your development. Like, for example, if you have manual configurations involved with rolling out new services, then this will become a bottleneck for your engineering teams and so forth. So automation is key, and you should aim for having a monitoring in place that automatically can react to all the types of changes that happen in your environment. And one of the other things that became harder, and I find this particularly interesting because we spoke of health checks a few minutes ago, is that health checks are now a commodity, and modern runtime environments like Kubernetes provide health checks out of the box. However, health checks are not sufficient anymore to represent the application's state, right? If you only have a single deployment, then it's kind of okay to say, if this deployment responds with 200 okay, it's fine. If it doesn't respond anymore, something's seriously wrong and I need to be alerted. If you replace the single deployment with a collection of dozens or hundreds of microservices, it's not so easy anymore to define what's a healthy state of the application and what's not healthy. And in order to solve this, there are new types of data emerging in modern monitoring systems, and these types of data are metrics and distributed traces. And so in the next two slides, I will introduce what metrics are and what traces are, and then we will see an example of how they are used in a typical application dashboard and how these relate to each other. Let's start with metrics. So metrics are actually very easy to understand. Metrics are time series data. So you see an example in the top right of this slide. You have the x-axis, which represents the time. You have the y-axis representing the value. And a metric is basically a value changing over time. So the value is going up and down. And those metrics are actually well better suited to describing the application state than simple health check results. And to give you an example, a typical metric that you often see in monitoring is latency, right? For a specific HTTP endpoint, you want to know how fast does it respond, right? And then you can use this metric information and define service level objectives with it. You can, for example, define that for my specific HTTP endpoint, I want that 95% of the calls are responded faster than 100 milliseconds, and only 5% of my calls may be slower than 100 milliseconds, right? That would be a good definition of a healthy application state. And this is a definition that plays well with highly distributed applications, right? And if you have this type of definition, this type of server level objectives that you can use to define what does it mean for your application to be healthy, then you can use this as a basis for defining your alerts. You can say, if my service level objective has been violated for, say, at least 5 minutes, then I want to be alerted. I mean, if for 5 minutes, more than 5% of my calls were slower than 100 milliseconds, then something is seriously going wrong, and I want to be alerted about that. So that's the type of way you define alerts for modern distributed applications. And an interesting aspect about these metrics and metric-based alerting is that those metrics are in many cases easy to understand and easy to use, right? You see your latency metric and you know what it means. But if you look under the hood, what it actually means to provide that data, like the work that's taken by your monitoring system, it's surprisingly subtle and complex, right? And the things that make it complex is, first of all, if you want to have the latency of a specific HTTP endpoint and you have a system that dynamically scales out. If load is high, it starts more instances of your particular service. Then if you want to know the overall latency of your endpoint, the monitoring system needs to aggregate the latencies of the individual instances providing this endpoint, right? And this, of course, this horizontal aggregation that changes over time as services scale out or scale back again. But apart from this horizontal aggregation, there are also vertical relationships. And with vertical, I mean that imagine your service level objective is violated, like at a given point in time, uh, say uh, more than 5% of your calls take longer than 100 milliseconds to respond. Then what do? You basically want to look at your metrics and related metrics and try to figure out what happened. And so you maybe first you see that your service is a Java deployment in a servlet container, right? And then you see, okay, it's responding slow for some reason. What you want to do is you want to drill down the system stack. You want to see, okay, this Java deployment is running in a servlet container. So let's look at the servlet containers metric. This is running in a JVM. So let's look at the JVM metric, like garbage collecting activity, right? The JVM is running in a Docker container. So let's look at the Docker containers metrics. Or this Docker container is running on a physical Kubernetes node. So let's look at the node metrics. And maybe somewhere down the stack on the physical layer, you see, oh, this one has, I know, disk IO that's total overload. And maybe this disk IO is related with why the service responds so slowly. And so you have both dimensions. You have this vertical dimension and the horizontal dimension, and both dimensions change over time. The horizontal dimension changes when services scale out and back again, and the vertical dimension also changes because your Docker runtime platform might at one point decide to kill your Docker image, kill your Docker container, and schedule it again on another physical host. And then you still have the same image providing the same service running in your cluster, but the underlying association with the hardware changed. It's all of a sudden running on a different node, right? And this is, if you want to use your metric to do root cause analysis or to have these aggregations and to see what's going on, then basically the underlying monitoring system needs to take care of all these relationships. And there are different ways how different monitoring systems solve these. What we, for example, do at Instana is we actually explicitly model those relations in something that we call a dynamic graph. And this dynamic graph has all the relations and it changes over time. So you can basically scroll back to any given point in time, look at the horizontal dimension, look at the vertical dimension, and relate all different types of metrics that we collected at this point in time with the configuration as it was at that point in time. Good. So that was a quick introduction to metrics. So basically, metrics are time series data and are a good way for defining what it means for your application to be in a healthy state. The other type of data that is often used or more and more used in monitoring are distributed traces. So distributed traces are about understanding the distributed system behavior, right? You have a call coming in to a service A, this service A calls service B, this service B calls service C, etc. And you want to know which services are involved with actually responding to that incoming call. And the way distributed tracing works is initially, when a new call is generated, a unique identifier, a random identifier is generated, which is called a trace ID. And whenever one service triggers a call to another service, be it synchronously or asynchronously within the context of resolving a specific call, then the trace ID is also passed on to the next service. How is this done? Depending on the protocol, of course. In many cases, services communicate with each other over HTTP, and then obviously the trace ID is passed on as a additional HTTP header. But of course, other communication protocols have their own means of attaching metadata as well. For example, if you have message queues, you can use message queue metadata to transport the trace ID. Right? And then every individual service, of course, knows how long it took to respond the incoming call, which outgoing calls were triggered, how long it took to respond the outgoing calls. And the monitoring systems collects all this information together with the associated trace IDs. And then in the backend, we can bring all this information together and create a distributed call graph describing the distributed system behavior. You see an example representation of a trace in the bottom right corner of the slide. So what you see here is we have the long blue line, which is the initial GET request going into a system. And then the first thing that happens is the orange stuff where the system triggers a database request, and then a millisecond passes where it obviously processes the result, and then a new GET request is fired to another service, and this other service has again such an orange bar indicating a database request, and so on. So you can, I think you get the picture. You understand which service triggers which other service for resolving a call. And this is key for understanding your distributed systems behavior. If you enable your engineering teams to ship new services into production, if you have a dynamic changing environment, you will not have, your big PDF document describing all the relationships of the different services. But at some point in time, you need to understand what's happening, and traces are a good way to give you the real picture, to show you what's actually happening in your distributed system. And of course, this data is totally necessary for root cause analysis. For example, if a service responds HTTP 500 internal server error, if you have tracing enabled, you can navigate to the trace of this call that produced this error and then drill it down. And then you see, okay, this service called another service that responded HTTP 500, and this service tried to access a database, and there was no database connection available, and this is what failed, right? And if you have those errors, happening a few levels down the distributed call stack, this is virtually impossible to figure out if you do not have tracing in place. But if you have tracing and can just click on an example call and see everything that happens, it's very easy. You see immediately where the actual error happened and where to look and what to look at to fix the error. So, what are the things to watch out for? What are the things happening under the hood that make tracing maybe a little bit more complicated than it looks? I mean, the first thing that's really important is if you want to use tracing, you should find a way to have tracing enabled for all of your services, right? If you are running a mix of some legacy services and some new services, and you end up with a scenario where the new services have tracing enabled and the legacy services don't, then your traces will be rather useless, right? Because there are gaps whenever a call is happening to the old world, and you will never get the real picture, right? And so in order to have everything instrumented with tracing, you should have a monitoring system that allows you to instrument legacy services with tracing at runtime, right? There are different ways how to do this. Like, for example, in Java, typically those systems have Java agents that you can attach to the running process and that then instrument your service with tracing, and all of a sudden your legacy service provides tracing data. And of course, monitoring products kind of support all different types of programming languages, frameworks, and stuff, so they can really attach to a lot of things. And chances are good that everything you have actually running in production is supported, and then you have a total coverage for tracing across all your service landscape, right? So avoid gaps. Try to find a way to instrument everything with tracing. And then, of course, as your landscape is more complex and has maybe a lot of services involved with monitoring, then grouping becomes important, right? I mean, for some people who really want to understand what's happening within a cluster, it might be good to have the full picture and to see everything. Maybe for other people who just, treat your services as a black box, it would be good to say, I'm only interested in ingress and egress, only in incoming and outgoing calls, but I'm not interested in what happens in the actual cluster. And so I want to, group that together and treat it as a single service, although it like under the hood is implemented as a collection of multiple services. So, but that's kind of, yeah, if your environment becomes more complex and you want like ways to structure things. Good. So distributed tracing allows you to understand the distributed system behavior, which services are involved when responding to a request. So now that we had a quick introduction in the underlying data that's typically used in application monitoring systems, let's look at an example and see how this data plays together. And the example here that I came up with is this big box in the middle saying 120 milliseconds. So if you create an application dashboard, this might be a typical number that you put on your application dashboard, right? And the meaning of it should be that this is the 99th percentile of your latency for your application, meaning that 99% of the calls to your application are responded faster than 120 milliseconds and 1% is slower than 120 milliseconds, right? Typical data that you see on your dashboard. And as mentioned earlier, this is also a good way to describe your system behavior. And if you understand the desired performance characteristics of your systems, it's easy to look at this number and see if this is good and healthy or not. So, but the interesting thing is you have this single number being displayed on your dashboard, and the single number is very easy to understand and to work with. But what's actually happening under the hood so that the monitoring system comes up with this number is a lot more subtle and a lot more complex than you might initially think when you just see this number and use it, right? And the first question, if this represents the latency of your application, is of course, what is an application? And interestingly, the answer to what is an application is in most cases not so much a technical issue, it's more an organizational issue. If you have an engineering team and you ask them what application they want to monitor, they would typically define the application as the set of services they are responsible for. And this is, of course, something that's, can be more defined in organizational terms and not so much in technical terms, right? And then you have this aggregation of all the services that your team is responsible for. And the question is, how do you actually get the data? How do you get the latency data of your services? And, I introduced to you metrics and traces as kind of two independent entities. And of course, 99th percentile of latency is a typical example for a metric. But if you look at it, the data that you need to come up with that is all contained in the tracing data. So if you have your services instrumented with tracing, you basically have this information, what calls are coming in and how long did it take to respond to those calls. So the monitoring system can take your tracing data and derive latency metrics from it. So it's enough to instrument your services with tracing if the monitoring system is smart enough to derive latency metric from the tracing data. So tracing and metrics are not independent of each other. And there's another reason why they are not independent of each other, because if this number is too high, if you say, wow, 120 milliseconds, I'm expecting 60 milliseconds here, so let's have a look what happens, then you want to click on this thing and see example calls going on that took those 120 milliseconds, and then you want to click on them and see the associated traces, right? You want to see, okay, this service called that service called that service, and here was all the time spent. So you want to know where the performance loss is actually happening, where down the distributed call stacks. So metrics and traces are related to each other. First, because you can derive metrics from traces, and second, because you want to navigate back from your metric data into the tracing world to do root cause analysis. Apart from that, of course, I was talking a lot about metrics and traces now because those are kind of the new things in monitoring and the things that change the way monitoring systems work. However, there are old things in monitoring that are, of course, still important. Like, for example, profiling. Like, if you figure out that performance is lost at some point, um, you might be happy to have profiling data of your application, and enabling profiling for your application, if you have like sample-based application profilers, can be done without much performance overhead. And then if you have that and you see, okay, in this service we wasted more time than expected, then you can look into the profiling data and see, okay, it was actually these methods and these methods, and you can, engineers can figure out where in the code the actual performance degradation happened. Or logging, right? The good old logging is also something that's of course still relevant. And if an application writes a warning and error, and if a service writes a warning or error log, and if this log line is written in the context of serving an actual HTTP request, for example, then it's good to be able to navigate from your trace data to this particular log line. For example, if you have your trace and you see, okay, this service responded 500 internal server error, and the developer was nice enough to write a log line describing what actually happened and what went wrong, then you want to, within your trace, see the associated log span where you see, okay, this error was logged in the context of responding to this specific HTTP request, right? And so all these different types of data and signals that you have are aggregated together and come together, and then you have this easy to understand dashboard that just says, okay, 120 milliseconds, but under the hood, it's rather interesting and complex, how all those different wheels play together and how they enable you to navigate in all types of directions and understand what's going on. Good. So far, I spoke a lot about technical challenges, but of course, apart from these technical challenges, I cannot, I at least need to mention that there are organizational challenges as well. I mean, that's definitely an important topic and it should be worth a talk on its own. But I think it's good to focus first on the data and the actual technological capabilities of monitoring systems, because once you understand them, it's also easier to reason about what people actually do with it and how people should use these things. But of course, if you go from, a classical development and operations organization into an organization where developers can create their own Docker images and ship them into production, then of course those software developers get a lot more responsibility for actual runtime operations, right? They own the images running in production, and they have responsibility for making sure that the performance of those of their services is as expected. And so the software engineers typically get highly involved in runtime production monitoring of the services that they implement. And also on the operation side, there are new roles like DevOps and SRE dealing with these constant rate of changes and with this automation. And there are a lot of new processes coming up in that area. And if you're interested in that, there are, of course, those nice O'Reilly books published by Google. I think it's now 3 of them, and all of them are available for free on Google's webpage. So if you want to learn like if you want to get an in-depth understanding in processes and challenges of monitoring highly scalable distributed systems, then this is definitely worth reading. Good. Half an hour is almost over, so let's wrap things up. Docker enables dynamic, distributed, scalable, polyglot applications, and this, of course, requires new approaches to monitoring. One of the keys is that you need to automate as much as possible in order to deal with the constant changes going on in your system. You cannot have manual checks. And the other thing is that there is new type of data that modern application monitoring systems use to build their functionality on. And this new data are metrics and distributed traces. And if you understand what they are and what you can do with them, this will definitely help you define a reasonable monitoring strategy for your microservice environment. And of course, you need to adapt your teams and roles to the new world because it has not only an impact on technology side, but also an impact on the organizational side. So this is it for me. I think I will hang out in the Slack for a while. So if you still have questions or want to discuss things, go ahead and let's chat. And yeah, I wish you a lot of fun with the rest of the talks in the DockerCon live conference. Thanks a lot for listening. Bye.